we start?
Okay, we are good to start our QFT string seminar. And today we are happy to have our foreign visitor Mikhail, Professor Mikhail Alfimov from Higher School of Economics and Lebedev Physical Institute of Russian Academy of Sciences. Higher School of Economics, whatever the strange name. No, yeah, but
No.
Anyway, let me make precise. This HSC is one of the main mathematical centers along with Steklov Institute in Moscow. And anyway, he's working in the mathematics department. Russian Academy of Sciences. Okay. Yeah.
Sorry,
and,
otherwise it would be too long, this
right.
affiliation.
So let me maybe just say a few words. Mikhail Alfimov, he graduated under supervision from École Normale Supérieure from Vladimir Kazakov and Grigory Karchemsky. And his main area is sigma models and supersymmetric sigma models, wall-sheet integrability, and integrable quantum field theories, because due to his close interaction with our common teachers, like including Zamolodchikov and Fateev. So, and today he will tell us about two-dimensional conformal field series defined by screening charges and their dual description in terms of the 2D deformed integrable sigma models. So, please, Misha.
Okay, so I can start, right? First of all, thanks for the invitation for this beautiful place. Today I will speak about the general topic of dual description of the so-called 2D deformed integrable sigma models, and actually this dual description is based on 2D CFTs defined by screening charges, so that's why it is important to study this thing. My talk will be based on a series of papers with Boris. Sorry. Okay, on the series of papers with Boris Feigin, Ben Huare, and Alexei Litvinov, and some ongoing work with Boris Feigin. Okay, so first of all, a few words about the motivation for such a study. We know that integrability preserving deformations of O3, or nowadays it's known for ON sigma models, deformations, I mean, for example, the eta deformation, are known to admit the so-called dual description in terms of some theory of bosons and Dirac fermions with exponential interactions. So it's some kind of Toda-type theory. One of the most well-known examples of such a description is the dual description of the so-called sausage model. So this O3 model, when we have the O3 model with the spherical target space, and we deform the target space in a way that it preserves at least classical integrability. Then we can, on the other hand, we can assume that this model, we know this model is classically integrable. We also assume that this model is quantum integrable, and from this knowledge, we can, solving the Yang-Baxter equation, we can find the S matrix of such a model based on its symmetry. And on the other hand, we can deform this S matrix. I will show you the precise formulas on this. And then we can, on the other hand, we cannot calculate this S matrix directly from the sigma model action. But on the other hand, we can write down some theory of Toda type. So it's basically some free theory plus some exponential charges, from which we can just directly calculate perturbatively this S matrix. So this is how this dual description works. And it appears that we can actually extend this dual description for many more cases. For example, to O4 and ON sigma models. This was done in the papers by Fateev in 2004. And then it was generalized to all ON cases by Litvinov and Spodeneyko. And I'm again in 2018, and I'm again talking about the so-called eta deformation. So it's the deformation which basically violates some of the ON symmetries. For O3 model, it just the following thing happens: we just a little bit extend this sphere, and then we have still U1 symmetry, but lose all other symmetries, at least explicitly. Okay, and on the other hand, for people who are well familiar with, for example, the study of n equals to 4 and ADS 5 crosses 5 duality, we know that we can again solve the Yang-Baxter equation with the symmetry corresponding to the ADS5 superstring, and we can deform the solution of this Yang-Baxter equation. Just write down mathematically the solution, the Q deformation of such a solution. And so we can also do this for many other, for the other types of integrable superstring models like ADS4, ADS3, and so on. But what is nice about this Q-deformed solutions of Yang-Baxter equation, they share all the same property. If you take this parameter Q equals to -1 or some root of unity, this S matrix becomes proportional to the graded permutation operator. Okay, I will show you just explicit examples for O3 and OSP12 case. And what does this mean physically? Physically, this means that probably in the parameter space of the theory, there exists some special point in which this theory becomes just free theory, right? So this is the key feature for building such a dual description. So this means that probably we can understand our integrable sigma model as some integrable deformation of some free theory. Or in some cases, it can be understood as some integrable deformation of some conformal field theory. I will just show you now the simplest example of such case. Our strategic aim is to build such a dual description for this deformed superstring models, because they also share this property of when you take Q equals to -1, the S matrix becomes very simple. But there are, when going from this ON case, there are three main things to do on the way to achieve this. First of all, we remember that for this ADS5 case, this if we write the cassette construction for such a superstring theory, it contains PSU 2,24 in this in the numerator. So it's a supergroup, and we must somehow include this odd degrees of freedom to the dual description. And the most natural candidate for such a generalization is considering, instead of sigma models with the sphere target space, consider the sigma models with the supersphere target space, which is the OSP M2M sigma models. And this will be the main topic of my talk today. But there are some other difficulties. Then we have to adapt this construction to describe sigma models with non-compact target space, which is ADS5. And we do not know yet the examples of the dual description with the non-compact target spaces. And also the superstring theory, it has the reparameterization symmetry, which requires the gauge fixing, and we have to somehow include this reparameterization symmetry into our dual description of the sigma model, of the superstring model. But nevertheless, today I will concentrate on this point. So let me remind you some things about the OSP sigma model. So let's consider the for now the undeformed OSP sigma model. What does this mean? It means just the generalization of this ON sigma model when, as a target space, we have the supersphere. So part of the coordinates in our space are just odd coordinates. This means this is given by the symmetric space sigma model on this supercassette. This model is known to be classically integrable as well. You can write down the Lux pair as in the case of ON. And the action is given by this expression. So here R is the radius of the supersphere. And here we have J plus, J minus, which is given by this expression, this Maurer-Cartan form. And P is the projector on the grade 1 superspace. I do not want to go for now into these technical details. In the subsequent slides, I will just show you the simple way how to write down the action of the OSP model directly from the ON model, just replacing part of the coordinates with of even coordinates with the odd ones. There is a very nice and beautiful procedure to achieve this. Okay, and what is important for us that this model has symmetry, with such a symmetry, has the following rational S matrix, which was found in this paper by Soler and Fritz-Kaufmann. And it's very similar to the ON case. It also consists of 3 terms. But with the following difference, that here, instead of just permutation operator, we have the so-called graded permutation operator. So in the elements of this graded permutation operator, when we have the permutation of two odd coordinates instead of +1, we have just -1. That's the difference. And we have some difference in signs in this term. I'm sorry, I always forgot the English name for it, but I think it's called something like when we. Okay. Nevertheless, I think everybody here knows how this looks like. In the case of n, it's just delta I1, I2 times delta J1, J2. Yeah, I'm sorry for forgetting this. Yeah. Okay. Anyway, you see that these factors in front of these terms they are very similar to the case of ON, except for instead of n minus 2, we have here n minus 2, m minus 2. And this is not a coincidence because, in fact, when I write the RG flow of such a theory, you'll see that if this expression is positive, then this theory will be asymptotically free. And when it's 0, it will be conform. What we are interested in only the asymptotically free case. Unfortunately, yet we're not able to build a dual description for the conformal or not asymptotically free case. So let's now assume that this is positive. So you see, this is the only difference, and the difference in the signs inside the permutation operator. And what's nice about this matrix, we can, of course, also build its trigonometric deformation as for the ON matrix. It was done by Bazhanov and Shadrikov. And I will not write here, of course, this whole trigonometric solution. It's very large. But anyway, if we introduce such a parameterization in this trigonometric solution, so here Q is the deformation parameter, and lambda is also can be considered as the deformation parameter, we see that if I send lambda to 0, I just restore this rationalist matrix. But something special happens if I send lambda to 1/2. In other words, q to -1. If I send q to -1, the S matrix becomes proportional to the graded permutation operator. And in the case of even n, this graded permutation operator corresponds to n/2 Dirac fermions and m bosonic particles. And in the case of odd n, it corresponds to the same plus 1 boson. So let me show you the simplest cases of this kind. Here is the O3 example. So you see, if I normalize by the central element, in this point, lambda equals to 1/2, it just becomes the graded permutation operator, which corresponds to one Dirac fermion and one bosonic particle. Okay, and here we have some corrections, which we can actually obtain from this dual Lagrangian of the sigma model. And next example, this is not actually asymptotically free, but I mean mathematically, in principle, the structure will be the same for any OSP n2m case. So you see here, if I put lambda to 1/2, it means that I have just the permutation operator, not graded, which means that I have, you can consider it to be one bosonic particle with two components and one additional bosonic particle. Okay, so what does this mean physically? This means physically that this theory at this point looks like some free fermion plus free boson. And these corrections are generated by some integrable perturbations. And this guy also, it looks like some free bosons at this point plus some integrable perturbations. Okay, so let me write the result. In this case, the result is the following. What is our task now? So now we have this trigonometric deformation of the R matrix, and we have to write both formulations, sigma model formulation for this R matrix and dual Lagrangian formulation. So what are the natural candidates for this? The natural candidate for the sigma model formulation is the eta deformation of this model. So here I wrote this eta deformation metric, which is the famous sausage metric. And you can observed a nice property of this metric. So if you analyze the RG flow of such a metric, you'll see that in the UV limit, kappa flows to unity. So here, if kappa is just 1, actually here kappa is proportional to the deformation parameter, which is just I eta. If you consider the eta deformation, it's just I eta. So it's kind of analytic continuation of this eta deformation. So here, if kappa is just 1, you see that this disappears, and this doesn't contain any phi. So if I just do some variable transformation for R, I obtain nothing else but the free theory. So in the UV, at least we know that this guy flows to the free theory, which doesn't contradict what we expect from this special point of the S matrix. And on the other hand, what was done by Fatiev, Onofriz, and Molodchikov, they wrote this Lagrangian for the dual description, which contains 2 bosonic fields yet. And it looks like some free theory perturbed by some exponential charges. So if you look carefully at this action, this first 4 terms is nothing else but the so-called sine Liouville CFT. And these 2 guys can be considered as the integrable perturbation of this CFT. Right? And the last term, it plays the role of the counter term. You can easily understand this by taking the OPE of, for example, these 2 terms. It generates exactly this term, and these guys generate this term, and all the cross OPEs, they generate the others. And what is nice about this action, it doesn't contain any other counter terms. You do not need them to counter the divergences. Okay, but this is not the end of the story. We know that in this special point for k equals to -1, we have 1 free boson and 1 free fermion. So to restore this S matrix of the theory. And to achieve this, we can apply the Coleman-Mandelstam boson-fermion duality for this action. And you see that we arrive to this relatively simple action for the dual Lagrangian of the theory. And as you can see, it contains this kinematic part of free boson and free fermion, some 4 fermion interaction, and this term contains the mass term for the fermion, and this guy contains the mass term for the boson, but they also contain the interaction. So you can consider B to be the coupling constant. And then if you identify this B squared with lambda in this way, actually you can write down even the exact formula. So let me, where is the chalk? There, okay. There is exact formula for this connection, which is this. So you can just check order by order in B squared that this Lagrangian gives you the next corrections to this. So this at least proves one side of this duality. With the other side, we have still to make some connection, and this requires some additional work, and I will partially tell about this today. So anyway, what is my aim? My aim is to generalize this kind of description. This is the simplest example of it for the other deformed integrable sigma models. And in this talk, I will explain you how to do this for OSP sigma models. Okay. So as I said, the starting point for such a description is considering this theory as some integrable deformation of the CFT defined by screening charge. So with this example, you can easily see this. Actually, you can understand this even as the integrable perturbations of different CFTs. So for example, you can take these 2 screenings with this free action, it will be still the CFT, but perturbed by these screenings. So you can consider any pair of these screenings to be the perturbation of this theory. And in fact, even if I think if I take, okay, I have to think about this, but maybe if I take even 3 screenings, it will be still CFT. I think it will be not, okay, yes. Yeah, they're here. Why? They're just in the exponent. When I perturbatively analyze this action, I just expand order by order in B squared.
They don't blow up, they don't go.
No. No, this term handles all the divergences in this action. Yeah, and this phenomenon repeats in all other actions, in fact. So for this dual description, you have finite number of counter terms. And this is very nice. They actually generated from this. You can see that this e to the I beta phi, it corresponds to this fermionic fields, and these divergences, they appear from these fermionic loops. And if you just mnemonically multiply these guys by one another, you'll see that they generate exactly these terms. Yeah, it's a very nice calculation. You can just check it and see that it restores this R matrix. Okay, so let me probably start just underline some tips for looking for this dual description. So first of all, we have to actually establish the connection with the sigma model action, which is not actually simple. I hope to talk about this in my next talk on Monday. And this theory has to be renormalizable in the certain sense that we add some covariant counter terms, in the sense of like Friedan did in his PhD thesis actually. And in case of ON and OSP end-to-end sigma models, we can check this by solving the RG flow equation that just in the leading order, in the scalar curvature, only the couplings change in the action. And we can actually do some certain coordinate transformation for the action of the sigma model and see that it still looks like something free plus screenings of some different type, which actually equivalent to these exponentials on the previous slide. I will show this today. The next point is that our dual theory, we find it as an integrable perturbation of some free theory. And of course, and this perturbation is determined by some set of screening charges, which has to commute with the integrals of motion of the theory. So what does this mean? We can use these exponential charges to find the integrals of motion of the theory order by order in the mass parameter. So what does this mean? If you look at, on the previous slide, we can just use these screenings to generate the integrals of motion in the first order in M, in the mass parameter, and then repeat this order by order. Of course, this is a very hard task, but for some simplest examples, this was done actually. It was checked that these screenings, they determine the set of integrals of motion, and actually vice versa. If you have some integrals of motion of the theory, they determine the screenings. Yeah, and as I said, in the case of O3 theory, there are 4 of them. They depend on the continuous parameter, and beta is just square root of 1 plus b squared. Yeah, this I already said. And this picture, it repeats for the other integrable sigma models, so we can act in this way. And what is important for establishing the connection with the sigma model action, the sigma model action in the UV limit generates some set of screenings, which will be shown to be equivalent to this set of 4 screenings, which establishes the connection with this dual description of the sigma model. Okay, and the last point, how to look for the specific ON and OSP end-to-end sigma models, is to find the screening description of the sigma models as integrable deformations of this cassette CFTs. So in the case of ON theory, it's the SON by SON minus 1, and in this case, it's this guy. And this W, it depends on N, M, and B squared. This is the level of this theory. So in the subsequent slides, I will show you how to find the set of screenings for these CFTs, and then how to deform these CFTs to obtain the dual Lagrangian. Okay, so first of all, some introduction about the CFTs defined by screening charges. So let's consider some n-component holomorphic bosonic field, which is normalized in this standard way. And these alphas, which are called the screening lengths, they are the vectors in the space of this scalar fields phi. Okay, so in the previous case of O3, we have the two-dimensional space of these screenings. We can define some vector alpha algebra as some set of currents of integer spins such that they commute with the screenings. In our case, we're interested only in the case when we have s equals to 2 and then s equals to 3 currents. Actually, this problem was solved. So Alexey Litvinov and his co-authors, they found all the sets of these alphas which give you the spin 3 current of this kind. They classified all the solutions. And so let me start from some simple fact that for generic alphas, for generic set of these vectors, let's say we have the n, capital N of these vectors. So in the previous case, it was 2 of them. When we have signed Liouville CFT, we have 2 of them. And for generic alphas, we always have the spin 2 current, which is nothing else but the stress energy tensor of the corresponding CFT. So here, rho is expressed in terms of these alphas in this way. You can just solve this. This very nice exercise. Just take this expression, write W2 as some polynomial in the operators of Heisenberg algebra. Just check it, solving some linear system of equations. You will find that this is true. And this is the central charge of the corresponding theory, which is expressed again in terms of this rho. Okay. And what is important about this statement that will be important for us in the future, that for n equals to 1, we have this current. This is the simplest case. And you see that if I replace alpha with alpha check, I just obtain the same stress energy tensor. So this means this we call the dual screening with this length. And actually this dual screening can be generalized for other cases. So let me say a few words about the general solution. So there are 2 types of these screenings. If you solve the problem to find the spin 3 current, W3, of course, for generic alphas, they do not exist. But anyway, we can classify all the solutions. We can classify all these alphas, sets of alphas, for which this spin 3 current exists. And it appears that we have to divide the screenings in 2 types. The first type is the so-called bosonic root. For bosonic root, this length of the root is generic, so it could be take any value except for -1. For -1, this root is called the fermionic root, and I will not go deep into details, but the solutions to this expression are different for these cases. So you have to classify them in different way. Just speaking it shortly, in the case when it's bosonic root, this additional current always takes this form, which can be expressed on the value of stress energy tensor on this parallel part of the field, which is parallel to the screening, to the given screening. And this is the orthogonal part of the field, which depends here. And in the case of fermionic root, that's why it's called fermionic. We have the screening charge of this form, which is, again, if you remember the procedure of Coleman-Mandelstam duality, it corresponds to the fermionic field. So basically, this set of the commutant of this screening charge will consist of this kind of currents of psi. So then our current in this case takes this form, because only W2 and W3 are independent. Okay, but this is some technical details. What is important for us is the following. As I said, for the simplest case, n equals to 1, the same CFT can be described by different sets of screenings. So, for example, we have this alpha and alpha check, which is 2 over alpha. This can be generalized for the generic n case, and we have the series of different dualities between the screenings. So we can replace part of the screenings with the different ones, and this system of screenings still describes the same conformal field theory. First of them is this bosonic root duality, when we replace the bosonic root with the bosonic root of this length. So in the case of n equals to 1, it's 2 over alpha. Next thing is that it's called the Dress sigma model bosonic screening. What does this mean? So let's say we have a couple of fermionic screenings, and for them the scalar product is xi. So then you can show that this so-called dress screening, why dress? Because we have this prefactor. It defines the same CFT as this pair of screens. Okay? And the length of this dress screening is given by this expression. Another duality of this type is for the case when the scalar product of the length of these screenings is -1. It's a little bit different. So we have the whole family of the dual dress screenings. They have the same form, but the length is given by this expression. So nu here is just some arbitrary parameter. You can just show this by commuting with the currents. You can show that they give the same, they define the same currents W2 and W3. Okay, some details about this last screening, because as I said, the whole family of screenings dual to this pair. But in fact, if in the given set of screenings you have some additional ones besides these two, this actually fixes the form of this dressed fermionic screening. It's fixed in this way that beta 2,3 times alpha 1, so the scalar product should be -1, and then nu is -1 over xi. And also some other case, more complicated, which is also actually needed for our description of OSP models, but I will not go deep into this. Anyway, another important feature of this screening picture, how to replace them with the equivalent set of screenings, is the so-called fermionic reflection. This transformation is based on some Coulomb integral identities, so we can actually track this fermionic reflection on the level of correlation functions in this CFT. Just by some transformations of the integrals, you can show that replacing this set of screenings with this one gives you the same correlation function always. Okay, and this can be nicely shown on these pictures with the screening. So here the links, they depict the scalar products. So let's assume we have some set of screenings, right? And this is part of it. What does this mean, fermionic reflection? Fermionic reflection means that I transform the length of this screen in the middle to -alpha, and the neighboring ones, they just turn into alpha plus the length of this screen. What does this mean? So if I have here the fermionic screen, it turns into the bosonic one, and vice versa. You can check this by the direct calculation that this always happens. Or if I have here to the left and to the right of this one, if I have two fermionic screenings, they will turn into the bosonic ones. Okay. And the fact is that by playing these games, you can transform the set of the screenings corresponding to the given CFT to different forms. So there are many different sets of screenings which define the same theory. And then our aim is the following. We have to find the set of screenings which define you this dual description, which behaves well when this B goes to 0. So when we can restore this S matrix perturbative, right? And the other set of screenings, it has to give us the sigma model action of the theory. And this will show us that this duality really works, because these two sets of screenings, they define the same theory. So here is the answer to this question for this sausage model. As I said, the sausage model is defined by the set of 4 screenings. You can see them, and here I wrote their lengths in the space of the fields capital Phi and small phi. So here you can see I depicted the scalar products of these fields, and here the scalar product is -1. These links, they appear because this case of the sausage model is somehow degenerate. You will see in the next slides that for the ON case, it looks much nicer actually. And here I wrote the corresponding dressed bosonic screenings, which correspond to this link, to this link, to this, and to this link. So we have 4 of them. But actually, to have the equivalent set of screenings, we can take only 2 of them. This pair or this pair. And also the other requirement that this pair has to restore us the sigma model action in the UV limit. And it appears that only these 2, they give us the desired sausage sigma model action. So as I said, this set of 4 fermionic screenings defines the same theory as this set of 2 dressed bosonic screenings. That's why this duality works. You can check that both sets of screenings, they define the same set of integrals of motion of the theory. Okay, now let's extend, maybe say a few words also about this. Actually, you can also remove some of them. If you take only one pair of this, as I said, this corresponds to the sine Liouville CFT.
Sorry, Misha,
Right.
just to make precise, am I correct that at the moment there is not known some universality class or universal transformations that would be matching all possible dual descriptions in terms of some screening charts? Like you have one set, you say you can redefine
Well,
the same.
you can generate all of them and write them on the blackboard, but the general, in general
yeah, like
case,
if you have some deformation and you have some set of screenings, and then you cannot construct probably you don't know the universal transformations, which would bring you all other subcases of screen charges, which would in total be equivalent to the same theory.
But why do you need all the sets? You need only 2 of them. You need the one which behaves well when B goes to 0.
I mean all dual descriptions. There is one set
all
of
dual descriptions. This is a nice question. I think nobody really did this, even for the simplest cases. Yeah, but there are some nice features of these dual screenings. As I said, you can take a pair of these fermionic screenings and take it's equivalent to only this one. And you can show, and I will show this in my next talk, that this one dress screening plus some free theory, it corresponds to the DVV black hole action after some simple transformation. And also you can, for example, take 3 of these dress screenings, and this will give you the action of so-called lambda models. So this is another deformation of the O3 sigma model, which the deformation without isometries. Okay, but I mean, you want to generate all these dual screenings, right? That's what you want. This is a nice question. As I said, maybe it's worth studying. Worth studying all of them. Okay. Okay, so now let's now what is my aim now? My aim now is to develop the method to write down the set of screenings for any ON or OSP n-to-m sigma model. And to do this, let's first understand how it works for the case of O5 sigma model. So for the O5 sigma model, we have this set of 5 screenings. So you can see this kind of extension of this picture. And if I remove one of them, I get the underlying CFT of this form. So this is SO5 by SO4 with this level. I can actually remove any of these 4 screenings. This will give me basically the same CFT, but with different parameterizations of the screening charge. But what is important about this picture? So let's apply to this picture this screening transformations, fermionic reflections, and so on, actually in this case only fermionic reflections, in different ways. So we can apply it to the central node and get this picture on the right. Or we can apply it consecutively a couple of transformations. So we can see this diagram. Actually, both these diagrams, both these screening sets, they define the same CFT. They define the same CFT. And you can see some similarity with the Dinkin diagrams, of course. So this, and let me put forward some hypothesis based on this. So if let's consider the general ON case. In the general ON case, we have the CFT, which is SON by SON minus 1. Let me write the set of screenings, which consists of the Dinkin diagram corresponding to the numerator of such a case, then some fermionic screening, and then the set corresponding to the numerator. Actually, depending on the n is even or odd, it depends where the numerator, where the denominator. But anyway, we see the rule that if I take all the screenings except for one in this way or in this way out of this diagram for any ON case, then we exactly get the underlying CFT for the deformed ON model. And what is remaining for us is just to deform the corresponding CFT set of screenings by just one screening. And this will give us the dual description of the model. So it appears that if I, for example, take this diagram in the blue frame, apply some consecutive fermionic reflections to it, I just get this diagram. We call it sometimes balalaika diagram. Yes, so Russian folk instrument. And then if I take this one from the red frame and do again some set of fermionic reflections, I will arrive actually to the same diagram. So the last step to apply is just to add some deforming, we call it affine fermionic screening. Okay, I just can show it here. So here I just add one of them. It means that in this picture, let me probably show. So I get this. So this will be the diagram for O7. So just write the free bosonic theory, add this exponential charge, let's write down all the counter terms, and you get the dual description. Okay, now let's go to the OSP case. So we need to build a dual description for the deformed orthosymplectic SIBO model. For this model, there exists similar eta deformation, which was built by Klimchik and then by Delduk. So in this case, we just have to put this operator in front of this current J minus, in front of this Maurer-Cartan form. This all can be calculated. But here, in this case, of course, the small difficulty is that this section, in general, it contains some B field. But anyway, this difficulty can be easily overcome by some nice trick. I will show it a little bit later. So a few words about the Ricci flow of such models. We have a similar equation like in the purely bosonic case. So here, this is the derivative of the sum of metric and B field. And you see that here you have the Ricci tensor, and here are some forms which correspond to the coordinate definition. But this is really some technical details. Anyway, all this results in these differential equations for the coupling constants of this sigma model. So nu doesn't change, and this guy changes in this way. And you see here this expression n minus 2m minus 2 times 1 plus eta squared. And as I said, to build this dual description, we have to do some analytic continuation in these deformation parameters, and this leads us to the differential equation, which have this nice solution where nu is constant and kappa is minus tanh of nu times n minus 2m minus 2 times t. What is important? If n minus 2m minus 2 is greater than 0 and t goes to minus infinity, which means the UV limit, this kappa again goes to plus 1. And the same phenomenon happens, so this sigma model is close to something very simple in this limit, actually not free theory, but a CFT. Okay, so let's consider the simplest case, which is n equals to 5 and m equals to 1. In this case, as I promised, we can easily get the OSP n2m action from the OM model action. So it just for this we just need to write down the action. Actually, we have the odd n in the so-called stereographic coordinates. So this is a very simple procedure. We can write down the metric of the deformed sphere in this way, and here kappa k is given by this. And just to go to the OSP n2 case, we have to replace a couple of bosonic coordinates by the fermionic ones. Very simple procedure. And this also this OSP case has a nice property that it has different eta deformations, because we can replace different z's with this fermionic coordinates. At least in our case, OSP n2m, which means 07, we have how many? I think three different options, 3 different deformations. I will stop on one of them. So by doing this, we can obtain the Lagrangian of this sigma model. It's rather lengthy, but anyway, you can see that it contains phi1, phi2, r1, r2, and fermionic coordinate, which is psi a. So here is the action of this model. You can see this part is purely this part is, sorry, it's actually mixed. This part is purely bosonic, and here you can see some fermionic coordinates, but anyway, it's not very important at the moment. You can check that this action is one loop renormalizable, so its coupling constants, kappa and nu and kappa, they satisfy the differential equations from the previous slide. And we can take the UV limit of this OSP 5.2 sigma models by rescaling the coordinates in this way. And what we see in the end, we see that our action takes the form of some conformal field theory plus some exponential charges. So you can see it here. Here are the free bosonic fields. Actually, this guy can be shown to correspond to some CFT. So this first part, and this part corresponds to this dressed fermionic and bosonic screenings here. Okay. Another part, how to obtain the screening description for such a sigma model. To do this, we can actually do the same trick. We can start from the dual description for the ON model and build from it the dual description for the OSP N2 model. This can be achieved by the so-called blow-up transformation. What does this mean? We have to, in a sense, split the root, one of the roots of the diagram for the ON case, into 2 fermionic roots by using this procedure. So let's say we have this root alpha with this length, and it splits into the couple of fermionic roots of this form. So we just add one direction in the space of bosonic fields, which describe our dual theory. On the diagram, it can be depicted in this way. And here I just wrote the corresponding dressed fermionic screenings on this diagram. Okay, let's apply this to the OSP 5.2 model. For the case of OSP 5.2 model, we have, for the O5 model, we have this set of screenings. I already showed it to you. Let's apply this splitting procedure to this middle node. If we do this, we just obtain this set of fermionic screenings. So here you can see it's similar to that one, except for these products are -1, not just the scalar products are -1. So you can write down all the screenings on this diagram, including the dual ones, and from it we have to assemble the sets which correspond to the Toda type description and to the sigma model description. And this can be achieved. I have to, how many time do I have? 10 minutes. Okay, I think I will make it. Great. So this set of screenings corresponds to the sigma model descriptions. So what do we take from the previous diagram? We take this, we take this, and this screenings, 4 of them. If we do this, you can just write down the corresponding action. This is really some technical details. I do not want to spend too much time on this, but anyway, you just can write down the free part plus all these 4 screenings and their corresponding counter terms. If you accurately do finish all this procedure, fermionize part of the fields, we arrive to this action, which can be identified with the OSP52 sigma model action if we do some proper identification of the fields in the UV limit. Okay, so one part of the correspondence is built. Let's go to the another part. From that previous diagram, we have to take the set of screening charges which behave well in the limit b goes to 0. So this set of charges, this is very similar to the O5 one, except for the middle node is just the dress screen. This is the only difference. So here we do the same procedure again. Write down the 3 fields, write down all the screenings and the corresponding counter terms, and again we see that we have finite number of counter terms. So here you can see that just taking the OPs of them, you generate only finite number of them. I just didn't write them all of them at the moment because there are too many. Okay, and then doing some additional actions with this dual model Lagrangian, fermionize part of the fields, introduces some beta gamma system. Anyway, all of these are some equivalent transformations. We arrive to the dual Lagrangian of the theory. So you can see here one free bosonic field, couple of fermions, again also one bosonic fields, and you can check that this Lagrangian it exactly restores you the this integrable S matrix from the very beginning of my talk, in the OSP case, this in trigonometric case, just taking the expansion in this parameter b squared. I think there is misprint. Sorry, it should be minus here. Okay, so now let me finish with some general statement on all of this. We can extend this picture
Okay. Okay, questions, comments? People think maybe they check. People on Zoom can also ask questions, by the way. Okay, maybe I can make precise few things. Also, I had the possibility already to ask. But maybe you can show the slide of when you have been introducing this OSP52 Lagrangian. Yeah, probably. Yeah, probably this one. No, this one. So, yeah, I understand. So, am I correct that this theory is already, according to this Fatiev procedure, when you start with some sigma model, which is integrable at the classical level, yeah, and then you can supplement it, or if you want, deform or correct it such that it becomes consistent at the quantum level. So, yeah, that's what, because here the integrability is classical here, right? Yeah, sure. This is Lagrangian, just Lagrangian formulation of some dual theory. Yeah, but then the underlying S matrix obeys only classical integrability, right? That's what I'm saying, which satisfies classical YB, not the quantum. Okay. More points. Sure. Yeah, maybe one more point. Maybe it's illegal, but still, I'm just wondering. When you mentioned going to all the so far in the context, what people have been looking at are symmetric target spaces, like complex projective space. Now, have you thought about if you transit to still symmetric, like Grassmannian target space? Would it be still possible to, or anybody like Fagin or other, sort of having this description? I'm not asking about quiver description, which is probably at the moment not clear, but yeah, but that's very important. So that there is such a deformation. Yeah, but I see. That would be actually very interesting. Even there is probably nothing can be said about this non-symmetric spaces, like flag manifolds. Classically, there are examples which are classically integrable, which are classically integrable but not quantum, right? Okay, thank you. Okay, if there are no further questions, let's thank Mikhail again. And just to advertise, if anybody of you are very welcome to come, because Misha will give kind of supersymmetric extension to this and some more comments of the part 2 sigma models, which he will speak on Monday. And he will also give a talk on Tuesday, which will be like a different topic, which related to what is called, if you want, checkerboard CFTs or fishnet, the logic of conformal field series. And in this connection, there will be also what is called, when people look for special limit, in which applies also to n equals 4, where people look into this special excitation called Pomeron and in the BFKL limit.